Cool. Okay. Welcome for joining the 10th session at Hackaday for quantum computing. And since last week, we had some new community member joining, so that's the session number 2 for them. Welcome, everyone, and welcome back. So, as always, I start with this slide to show people where to find things. This will be shared on the Hackaday project page. And we're gonna spend roughly 30 minutes today and talking about gates. And we'll also do some coding exercise. We use the Q# documentation and quantum katas for the coding exercise. Last class, we had this introduction of quantum computing, but we also got into some of the conceptual topics such as superposition, and we talked a little bit about gates, which use linear algebra to use matrices to control vectors. And then we also did some coding, so all this is done through the Q# language. Today we're gonna talk a bit more about these concepts and code a bit more. So last time I showed you this block sphere, and I didn't really use it much and didn't really explain what a block sphere is, but this time we're gonna really get into that. So for mathematics representations of all kinds of numbers, complex numbers, real numbers, we can use a graphic way to represent them. So we know that when we were kids, when we started learning math, we can draw a line and use that to represent a real number. Then we learn about complex numbers. Then you can use these two axes to represent a number that contains imaginary parts. So this horizontal axis is your real number, and vertical is your complex number. In terms of vectors, we again can use a graphic representation. So last time I already showed that a state can be written in a linear combination of 0 and 1. And that is equivalent of saying that the state, it has a 0 and 1 state in superposition, and they have some amplitude in front of them to indicate the weight of these two states. A and B are amplitudes, and they just tell you how much of 0 and how much of 1 is in your system. And we also saw that the state could be written in a vector. So A and B are just the element numbers for these 2×1 vector. Since it's a vector, we can represent it in the 3-dimensional space. It has a unit. It has a length, unit length, and you can draw any point on this sphere to figure out what A and B are. So because it's in 3 dimensions in the sphere, the A and B are just written in terms of these angles relative to your axis. All you need is basically you have two numbers. So in fact, even though it is a 3-dimensional space, the surface of a sphere is 2 dimensions. So you only need two numbers to represent this 2×1 vector, which translates to two angles. You can write any arbitrary point on the sphere using these angles. So theta is the angle away from the z-axis. Phi is the angle away from the x-axis. It's just convention. And it makes it very convenient. We call this sphere a block sphere. Your qubit can be represented on any point on the block sphere. And when you manipulate it, when you change it, say you want to apply a gate that would then change the number A and B, it just means that you're changing the location on this sphere. Just use a cleaner way to see everything again, turns out that your 0 and 1, these special states, exactly the same as classical states, are on these polar extremes of the z-axis. So the classical bits 0 and 1 are nothing but special cases in a classical, in the quantum qubit. Qubit can be anywhere on the sphere, and including the 0 and 1. So an arbitrary state is the same equation I showed earlier. You can represent it any number of theta and phi. So 0 and 1 are just two special cases. When theta is 0, so you have the state all the way up here, and theta equals to 180 when it goes down here is 1. If you can use a arbitrary angle, two arbitrary angles to represent a vector, then how you would manipulate that vector is to use matrices. You have two matrices. One is to change the phase phi, and the other one is to change the angle theta. So this is nothing but geometry. So a general rotation, you can write out how it would change theta and phi. You can have three rotational matrices. One is rotating around the z-axis. So your phi is changing, is rotating around z. And you can also have a rotation around the y-axis. Your theta is changing. You can write the same, similarly, Rx, which is rotating around the x-axis. But both Rx and Ry are just changing theta. And you can even actually just represent one of them using the other two. So this is the arbitrary matrices and arbitrary vector that tells you you can arbitrarily put any state on the block sphere and arbitrarily manipulate and change it. But we don't necessarily need to get on every single point on the block sphere. So for computational convenience, there are some certain locations on the block sphere that we like the qubit to be in. It is like using a set of coins. So all of these coins, you can have a combination of them to represent any number you want. So you have you don't have a coin for, say, $1, $2, $3. You don't have 1, 2, 3, 4, all of the numbers for each one coin for each number. You just need to have a small set of them, the minimum numbers needed, and make a combination of them to get to the number you want. But in here, the coin is just an analogy and is only got real numbers, because we only have, we could have some virtual money, I guess, but like we don't have imaginary money. But on the block sphere, you can have any arbitrary amplitude, which can be positive, negative, or complex. But the idea is that you want a small set of gates to get you to the points on the block sphere. So here are some commonly used gates. One is the X gate. They are called polygates. This X gate basically rotates from your 0 to 1 by 180 around the x-axis. So you see these amplitudes would just flip locations. You have Y, which is rotating around Y. It's very similar to X, but it adds on some additional phase. You then also have a gate that rotates around the z-axis. It doesn't do much other than putting a negative sign in front of your second element. Otherwise, if you don't have the negative sign, it's just an identity matrix. It doesn't do anything. So you should try the math. I think I showed this slide last time as well. that the Z and X gates are special gates resolved down from those arbitrary matrices. You should try the math to prove that the previous slide was true. And also the Y matrix can be represented using Z and X. So if you just have these two, you don't actually have to use Y. And we also last time showed the Hardeman gate, also called the H gate. It is a 2x2 matrix. It has a negative sign for the last element. What it does is to put your 0 and 1 to the perpendicular locations, and we call them plus and minus, because when you do that, you are splitting the 0 into a superposition of 0 and 1, and they have equal weight, equal amplitude. So that has a plus sign. We just simplify it and label it as plus state. And 1 is also put into a superposition of 0 and 1, but with a minus sign. So that location there is the minus state. So H gate is very frequently used. You will see it in almost every algorithm, and we will see a lot of that later. We also can divide those larger matrices into finer grids. So say you can take a square root or square root of 4 or 8 of the Z gate, and it just rotates around the Z axis by a smaller angle. These are also very useful gates. So if you use these commonly used gates, you can put your qubit onto locations that are very commonly used. So you can use a combination of them. So yeah, this is just to go through the math to show you what exactly H gates do. Try this at home. So H gate is putting 0 and 1 into plus and minus, but if you use those matrices, they are not directly rotating through this angle. It's actually first putting 0 to 1 and then back up to plus. So that's just some mathematical nuance you can check. If you want to use those arbitrary matrices for angle change, you will see that this is how H gates would behave. And an interesting thing about gates is that they not only can change your originally classical bits into superposition, then they become quantum gates. They can actually be used to, you can visualize it as they are changing your measurement basis. So I haven't talked about measurement in the last class yet, but people who have taken previous sessions, they have seen what measurement does, and that's what we're going to talk next time. So interesting about some gates is that they can put these states, basic states, to a orthogonal location. And if you just look at the symmetry here, the plus and minus are not different, really not different from 0 and 1. When you do a measurement using 0 and 1, you would obtain either 0 and 1 as your result. But there's nothing stopping you from doing a measurement using plus and minus as your basis. So that way you would obtain results in either plus and minus. They are exactly equivalent. There is a symmetry in the space. So here is trying to show you, say, if you have some cookie cutters in the shape of 0 and 1, they could be, you could use the H gate to put the cookie cutters into a different shape, say plus and minus. So if you are using these cookie cutters to measure your states, then what you will obtain are either the flower shape or the star shape. They will match to either of them. But there's nothing stopping you from using a cookie cutter in these two shapes and then also do measurement. You will get results matching these two outcomes. We'll talk about measurements more next time. So now we can go to do some exercises just to practice what we just talked about. Okay, let's get the katas going. So this is again the katas that we used last time, this link. Let me see if I can post this in the chat. So today, remember last time we did the superposition katas. This time we're gonna do the gate katas. So we go to the basic gates and open the kata in Jupyter Notebook. So people should be coding together with me. You should also do this step, opening up your browser and go to that link. First thing, you just run the package. So it has the necessary libraries opened in the backend. We'll just take a look read through these in your spare time. We'll just walk through these steps together. Task 1.1. So we get some qubit state, and it says if it is 0, then change the state to 1. If it is 1, change the state to 0. So we just talked about, and this first exercise always tries to give you a hint. It already tells you what the answer is. So here you just put in x cubed. So the nice thing about Q# is that it's really high level. You just tell the program to do the quantum operations. So then it also shows you a result. Then you can see that the amplitude would flip when it starts with a 0. It will end up to be 1. If it starts with 1, you could run it again and again, because it would give you random outputs. So this time it seems that the starting is, this one is 0, and your output will be flipped to 1. And it gives you also a simulation. The first one here is the desired state. It tells you what the outcome should be, and then the actual state is run by a simulator. So it also tries to behave like a real quantum computer. So later on, we'll see some of the results that you actually need to do multiple measurements in order to get the majority of the output to be what you desired. Let's go to task 1.2. It says that a qubit is in, again, it's always the arbitrary initial state, but it could be 0 or 1. So if it is 0, change the state to plus. If it's 1, change it to minus. So we actually spent quite a few minutes talking about this gate. So this is exactly what we need. So all you need to do is to do a Hardeman gate onto your qubit. And you'll see that it puts you into a state that's in between 0 and 1. So yeah, if you calculate 1 over square root of 2, you see the number. Task 1.3, sign flip. This is a sign flip challenge. So a qubit, again, now change the qubit state from the plus to minus. So do people remember which gate that is? On the left here, I'm showing you. So this Z gate exactly does that. So when you start with just A and B, you will get a negative sign for your one state if you apply a Z gate. That's it. It puts a negative sign. So this is actually funny that your desired state should be minus 0.8, but this one is giving the negative sign for the first one. So it actually added a global phase. The answer is correct, so it says it's successful, but then when you look at this output, it's the opposite as what you want, what you expected. It put a global minus phase. Because this is a simulator, it tries to simulate a real quantum computer, that's what could happen, and is exactly behaving like a quantum computer. So you could try to run it several times, and it seems that it's still giving this negative sign for the first one. Let's see what. Okay, now I run quite a few times in order to get the negative sign to show up at the bottom. But this is exactly showing you that it actually doesn't distinguish which one you have a negative sign there, because your amplitude could have a minus sign. So either you have a minus sign for the first state or the second state, it doesn't matter. All is needed is to have an opposite sign for the two. So you can run this many times, and you will get output that will randomly put the negative sign to either of them. That's quite interesting. Task 1.4. So what we're trying to do here, this is doing that arbitrary angle thing that I showed earlier. So now you don't have a nice clean 0 and 1, but you want, or arbitrary alpha and beta. They could be represented as angles on that block sphere. So it wants you to have 0. When it's 0, you will get these cosine alpha and sine alpha. If it's 1, it wants to be a minus sine alpha plus cosine alpha. So here, alpha is actually half theta. So I marked page number 5 will give us what we need. In this case, alpha is just your theta over 2. Because theta is the intrinsic direct angle away from the z-axis. All it's asking you to do is to put these two positions into either this one or this one. And if you look at these options of angular matrices, you will see that Ry will give you that outcome. So here you would do Ry. You're applying to your qubit, but you have to tell it to give it an angle. Because our intrinsic block sphere angle is theta, this case you would just represent your first angle as theta. So you just time alpha by 2.0. And that should do it. Yep. That's how you put these 0 and 1 states into these two states according to this matrix here. Now we go to 1.5. It's a phase flip. You are given an arbitrary alpha and beta, but now it wants you to give phase I for your one state. We have a gate exactly doing that. If you go to 15, I showed that you could have some gates that are just finer versions of those angular matrices. So this S state here is giving you what you wanted. All you need to do is to apply the S gate. And by the way, some of these commonly used gates are called a universal gate set. That's what people are trying to come up with, and having a set of gates that could put you in anywhere on the block sphere using a combination of them. Of course, the smaller number, the better, so you don't have to have so many gates for computation. And there are different choices. So if you do a search, just go to Wikipedia page, you will find all kinds of different ways to do universal gate sets. But some of these, like ST, Hadamard, XZ, and also the C0 gate that we would show later, which is a control gate, can be combined together to form a universal gate set. Okay, we're almost done with the single qubit gates. Task 1.6 is asking you to get a phase that is a complex number. So it's very similar to this one here, but it wants you to make it more general amplitude. So the point of the exercise here is not trying to get to the answer, but to show you how you can work on your own to find information that you need. So for task 1.6, you actually need to go to this documentation on the Microsoft Quantum Development Kit page. So if you search for Microsoft Quantum Development Kit, you'll find the documentations, and at the bottom, you have this API reference, and it has all of these Q-sharp libraries. There is a Microsoft Quantum Intrinsic that has a list of gates that you can use. I have already landed on this R1 operation. I think the website currently might be still down. Some of the equations are not rendering properly. So that's a known issue that we have already reported. If you go to this Microsoft.quantum.intrinsic, you may not see what I'm seeing right now. I'm actually on a different branch. I don't know if you guys can go to that branch to see this rendering, but we're trying to get this fixed. So bear with us for a bit. Hopefully it gets fixed soon. So I'm showing you what you are supposed to see when the website is not down. So there is a gate called R1. It gives you exactly what we wanted to do for that exercise. The diagonal just means that your first element, for example, this one here, this is the diagonal. So your first element is 1, your second element is e to the I theta, and the other two elements are 0. That's what it's telling us. So basically what you need is this R1 gate in order to put your system into this arbitrary amplitude. And it is called a phase change. So you would do R1, and again for Q, I think you just do alpha here. Okay, yeah, it's not that, nothing fancy. Okay, the last one, so beyond 1.8 is gonna involve multi-qubit gates. That's what we will be discussing in the next few sessions, as well as measurements that will get very interesting. So I think for the time, for the interest of time, I may not do this exercise with you. I will leave this as your own homework. What I also want to show people is that we have these certificates. I've been giving out these certificates to people who complete quantum kata. Choose any katas. This basic gates, you can try to finish it, but there are a lot of other very interesting katas in this GitHub. Choose any of these folders as one set of kata, and you can finish that, take screenshots or photos, post them on Twitter or LinkedIn at these hashtags and handles, so that I will see that you finished it. You will be given a certificate where you can print on anything. So there are already people who have completed this and got the certificate and print it on the mug, which is really nice. There's another tutorials you should definitely work through. These are a little different from the exercise that we did just now, which were more do it yourself, but these ones give you a comprehensive walkthrough of the thinking. So it teaches you, if you read through, you would familiarize the concept that I introduced in today's class. So you should definitely walk through this in your own time. Okay, last thing is there's some exciting activities going on. Dr. Sarah Kieser is doing the Q-Sharp Coding Live. She's doing that on Twitch on every Wednesday and Saturday. This is the link. You should definitely check it out and watch and try to code with Sarah. She's doing some of the more advanced coding experience that definitely recommended. We also have a Q-Sharp coding contest that's happening very, very soon. So you should register now. I can also post these links here. The slides will be shared on Hackaday. Yeah, don't miss the coding contest. This is your opportunity to contribute to quantum computing. Again, go ahead with the MS Learn modules. The first one is to write your first Q-Sharp program. So we actually just wrote a couple of them in today's class, but this one is helping you set up everything that you need for later quantum development. You install Visual Studio Code and download the QDK extension. I also already talked about this last time. Also, there's a survey on the Microsoft website, an opportunity for you to let us know what you want to learn. So that's what we talked about today. Next time, we're gonna talk about measurements and probably the controlled gates, so that you can experience what interference is. I may leave the control gates to later when we look at entanglement. So definitely next class is going to be very interesting if you haven't looked into interference before. Questions, please post on Hackaday project, and the past recordings are on YouTube and Hackaday. That's it for today. I'll also take a look if there's any question posted here. If people want to ask question right now, they can also jump on. Unmute yourselves. Thanks, Benjamin, for posting the basic gate link. Are there available notes from this and previous meetings? Yes, Theo, yeah, this is answering your question. All the past recordings. For some people, today's class is like a revision for them because they have been here for 9 classes. So they've seen Single-Qubit Gates For people who have missed those previous classes, those were more conceptual. We didn't do much coding together. So check out the earlier, more conceptual videos through these links. Thanks, Andrew. And Roberto, yeah, thank you. Roberto actually finished the class, finished this whole katas for Single-Qubit Gate. And he got a certificate as well. Can I share the link? Yeah, it's here. And this slides will be posted on Hackaday with the video recording. Okay, if there's no other questions, I would see you next week then. Thanks everyone for coming. Hopefully next time my camera works.
Thank you.
Yeah, thanks.